So, welcome everyone to Product Council today. You're very welcome to this session, which is going to be led by Mark Teehan. Mark came to us with a very interesting proposition around the adding a Mojaloop streaming service using the Apache Kafka stream processing. So the purpose of this is to enable real-time transaction processing for multiple use cases, the usual ones we talk about: fraud detection, marketing analytics, loyalty programs, etc., all without, and this is the crucial point, disrupting the critical payment flows. So that sounded like a really interesting idea, and we therefore thought it would be great to give Paul the opportunity to give Mark the opportunity to present it to Product Council and see whether perhaps we should be taking this through to a work stream. So this is the first step in that process. So I hope you'll give Mark your attention today. So I think that's it. Over to you, Mark, I think.
Thank you, Paul. Good morning, good afternoon, everybody. Today's talk is entitled Add a Mojaloop Streaming Service Using Apache Kafka Stream Processing. I hope you can see my slides okay.
Yes,
I'm
I
on.
can see them. Yeah,
that's great. I'm on full screen, so I can't see anything in the Slack. So please feel free to unmute or ask me any questions as we go along. Today's talk is actually based on a paper that I wrote earlier this year that's available on the Mojaloop Slack and GitHub with the same title, and it goes into a lot more detail about what I'm going to introduce today. So what I'm hoping that we'll all get out of today is to learn the first steps for extending Mojaloop for structured continuous data feeds for streaming applications. And that allows you to start thinking about building streaming applications on this foundation, like for fraud detection, for analytics, partner integrations, open data APIs, these types of things. First, a little bit about me. So I am actually Singapore-based. I have a small consulting company called StreamSend.io. I'm speaking to you today from Ireland. I'm kind of visiting family at the moment. But my background is with Confluent. Confluent are the company that was founded by the creators of Apache Kafka. I was their first employee in Asia for about 5.5 years, up until 2023. And I was Singapore-based, and I was kind of helping companies to build out Apache Kafka systems all across Asia Pacific. Prior to that, my background is all in data, mostly databases, but also in-memory databases and streaming systems for a number of different banks and also in some different transport and utilities. And my main areas of expertise are databases, Kafka, stream processing, enterprise data architectures. I should caution, I'm quite new to Mojaloop. Everything I've learned about Mojaloop is from the documentation, the wiki, the Slack, etc. I have run it. I've run the demo system, and I've connected to it and run the mobile generator and used that to sort of use as the basis for my recommendations today. So I have about 20 slides. It should take 30 to 35 minutes or so. We have plenty of time for questions as well. I'm quite happy if anyone wants to unmute and ask many questions along the way, because I may be making assumptions around things that are unfair. So stop me at any time, that's fine. You may have heard of Confluent also before, because Confluent was engaged for an architecture workshop for Mojaloop before in 2023. And this was really a review of a self-managed or an on-premise Kafka system in 3 sections: high availability, Kubernetes deployment, and how to optimize the Kafka. So I'm not covering any of this ground again. This was done by the professional services teams who sort of are very good at helping you to run Kafka systems in a more efficient way. I'm really looking at how to expand the role of Kafka to do more for your businesses. So there's very little crossover with this existing report. So my talk is really in 2 sections. The first is Kafka is more than a broker. Often it's viewed as just a messaging platform for ingesting data, but there's more to it. And for the second part, I'm going to drill down a little bit more and focus on stream processing in particular. So let's start with viewing that Kafka is actually a series of components. Mojaloop deploys Kafka really on the client and the server. You have various services or microservices that connect to the broker, and they produce and they consume. And this is very much core Kafka. You're probably running, well, hopefully 3 brokers, but possibly 1 broker. There's probably a zookeeper that it's connecting to for metadata, and then various clients connect to that, and they produce and consume to topics. A second important part of the Kafka ecosystem is the Confluent Schema Registry. And we blow this up a bit to see what I'm talking about. And it's really a data dictionary for a Kafka system. When I first started working on Kafka in the early Confluent days, I was quite surprised to find that while a topic functionally is similar to a table, they're different in one big aspect. A topic doesn't have any data definition. And you can imagine if you're deploying a database where you have a primary key and a club, and you don't really care what goes into the club, that's very much how Kafka systems tend to be deployed, where there's a payload and the payload has no structure. Often this is fine. And depending on the data types that you're dealing with, it may be more trouble than it's worth to start defining a structure. But Mojaloop and many of the systems using Kafka are money counting systems, and you're in governed industries, and actually structure is important. Governance is important. So Schema Registry lets you add a data dictionary to your Kafka system. The producers will basically start using schema IDs when they send the data to the Kafka cluster. And that schema ID is forever associated with that particular event in the Kafka topic. Okay, so it's a little bit different in that with a table in a database, it's always associated with one schema. Actually, a topic in a Kafka cluster could be associated with more than one schema, but generally one. But think of it as a data dictionary that you can optionally add on topic by topic for your cluster. We'll look at that in slightly more detail next. A stream processor is the second one that we're going to be looking at. And stream processor really allows you to consume data from a topic, do something to it, and then send it back to another topic. So it just creates a circular processing loop back into the Kafka topic. Okay. And finally, once you have these components in place, then it opens up the possibility of using Kafka Connect, which is another component of the Kafka system that makes it easy to get data in and out of your Kafka cluster without having to write applications using the Kafka client. So I'm going to just give a little bit more details and history in each of these APIs to talk about why I think that they're important for Mojaloop users. Anyone that's unfamiliar with Apache Kafka, it was developed in LinkedIn, really about 2009 and 10, but really released and donated to the Apache Software Foundation around 2011. And initially, it was a core messaging platform. It was a way of ingesting any amount of data onto a single platform where it could then be consumed by lots of disparate applications. And we're really disconnecting who's generating the data from who's consuming the data. That was around 2011. And then the various APIs started to appear a few years later. The first was the Connect API, because the board of the Apache Kafka project noticed that everyone was reinventing the wheel, and there's a lot of people simply mirroring database tables into Kafka topics. So the first connector that was written was a way of selecting from a database table in order to produce into a Kafka topic. And thus was born the Kafka Connect framework. It's a server that runs on a VM with various plugins and jobs, allowing you to stream data in and out of topics. That was created about 3 years later, and it's still a very widely used Kafka component. The Streams API came a couple of years later because of the fact that people were writing microservices repeatedly to do the same things, to transform data, to filter data, to join, to aggregate data. And they wanted to create a simplified way of doing popular stream processing operations. And thus was born the Kafka Streams API. 2017, the Schema Registry, the first sign of imposing governance on systems as it became to be used by more and more financial services organizations. Governance was important. We need to be able to audit these systems, impose change control on these systems, and the schema registry was the answer for that. 2018, we started seeing the next generation of stream processing. KSQL was released, which was an SQL interface for stream processing, which was fairly primitive. This was around about the time that I joined Confluent. And then this was revamped in 2020 with they call it a database, but it's really a database engine. The database storage is your Kafka topics. But similar to the original KSQL and its predecessor Kafka Streams, it's a stream processor for Kafka topics. And then last year, Confluent acquired Immerok, and they have started a much closer integration with Flink. And Flink is also a stream processor. There are quite a number of these. Spark SQL is a stream processor, as is Storm, Samza, some various other platforms in this arena as well. And they're all variations on the theme of being able to process continuous streams of data. And again, a reminder, welcome to everyone else that's joining the call. This will be about a 35 minute talk. Feel free to unmute and ask any questions as you want as we go along. Okay, the schema registry, as we say, it's an optional data dictionary for Kafka topics. You can define a schema over a topic on the assumption that all of the messages coming into that topic have the same structure, which is not always the case. And it's something that we do need to check before creating a schema. But once you've done this, it does some quite clever things. It allows you to evolve schemas. So you can have application development teams that are working on applications using the same topics, and they can change the topics. They can add columns or remove, well, I should say attributes from that topic without impacting other users of that topic, which is quite a sophisticated thing to do. And this is achieved using schema evolution. This really opens up the possibility of having separate development teams working on the same area of your Kafka cluster without stepping on each other's toes. It lets you put in change control. You can say, we're going to have a release for our topics this weekend, and here's what's going to change. Here's how we roll it forward, and here's how we roll it back. So just as you would for a database, you can have change control for your topics. There's no impact on your existing flows, as Paul pointed out. Everything I'm describing here is a way of extending the usage of your Kafka cluster in order to do additional things on top of the core processing that Mojaloop already offers. We're not talking about changing the functionality of any of your existing Mojaloop services. We're talking about extending and building on new applications that use the same topics and new topics. And there are performance benefits. By actually defining a schema, you no longer need to carry a lot of JSON information in the message to label each attribute and say, where it is in the JSON hierarchy. When you strip all of that text out, you can reduce your message size by, I've seen 50% is actually quite achievable. And it can also store the payload as binary. It can use better compression, etc. And 50% less means that your brokers have 50% less data, your network carries 50% less data, and all of these things. You can make your entire system much lighter than it was before by using a schema registry. And even though it's called the Confluent Schema Registry, it is free. You don't pay for it. They named the product the Confluent Schema Registry in the early days. It was fully open source with an Apache license. They changed it to a Confluent community license because there was a realization that some particular cloud providers were basically re-releasing the schema registry as a paid service. Confluent intended it to be free, so they changed it to a community license. But it doesn't cost anything for anyone in this ecosystem to use it. So you made a very valid question. Why not just change all of Mojaloop over to the schema registry and get a 50% headroom on all of your services? It's a bit more complicated than that because it changes the client. It would require recompilation of Mojaloop apps because they use standard JSON message envelopes for Kafka. So they serialize using either JSON or string. In order to use a schema registry, we would serialize using a different serializer. That would mean recompiling Mojaloop apps. So I'm not proposing this change. I'm not proposing that everything would change. I'm simply suggesting that the topics that contain messages from the Mojaloop apps can feed into new topics that have a registered schema and then offer all the various benefits we've talked about here. Perhaps at some point in the future, it may be considered by the core team to use a schema registry, but that's not anything that I'm proposing in this talk today. The third part of the Kafka ecosystem is a stream processor. So you consume from a topic, do some sort of processing, and produce back to another topic. So it's important to note that a stream processor is a compute engine that also writes back to the same Kafka cluster. Kafka Streams was the first stream processor. It's a Java library, so you have to write Java applications and have the entire full Java lifecycle that's required in order to use a Kafka Streams library. However, Kafka Streams is a very powerful library. And it does a lot of quite sophisticated operations, particularly for very high fault tolerance, scaling up, scaling down, storing of metadata. You can create massive caches of real-time data using Kafka Streams. Very powerful library that you can use at a very enterprise strength, and it's used by some of the very large organizations like Netflix and Uber, etc. KSQLDB followed a few years later, and it's an SQL interface over a stream processing engine. And then Flink is the most recent entrant into the stream processor world. A stream processor processes events as they arrive, not in batches. So it's a continuous flow. And we're looking at millisecond latency. So it's important to be realistic here. You're looking at hundreds of milliseconds of latency in general for stream processing operations. So probably 100 to 500 milliseconds. So 1/10 to 1/2 of a second in general for stream processing steps within a topology. It's certainly not microsecond, and it's certainly not single-digit millisecond. But in my view, for fraud detection or any anomaly detection type operations, this sort of latency is acceptable. It would not be acceptable, for instance, for high-speed trading or these types of super time-sensitive operations. And stream processing for all of these operations, it's scalable. So if you have a period of very peak activity approaching, a weekend or end of month or end of year, etc., and you need to be able to scale operations without tying up compute unnecessarily, then it's important that your stream processor is able to scale up for a weekend or a week or a month and then scale back down again afterwards without interrupting the processing operations that are happening on the platform. Okay, and then the final, a deeper dive on stream processors is KSQLDB. I'm recommending to use KSQLDB because it's stream processing for database people. My background is as a database person, years of doing Oracle and MySQL and Postgres. So select statements are a very natural way for me to sort of express processing logic. KSQLDB lets you express things like a transform, a filter, a join, or an aggregate using select statements. If you've ever written a database view, then you can write a KSQLDB stream processor. So you transform using select, upper of a name to change it to uppercase. Amount multiplied by 1.1. So all of the usual mathematical functions, these are transforms to attributes from your Kafka topic. A filter is simply a where clause. Where amount is greater than 1,000, I'm only interested in events in my topic where the amount attribute is greater than 1,000. And just like for a view or a select statement, you can make your where clause as complex as you wish with nested predicates, with and or Boolean operators, etc. A join, just like a database, joining two database tables on two different columns, you can join two topics on two different attributes. Now, this is a slightly different concept because we're talking about joining events the moment they are produced into the topic on two different attributes. So in all cases, one of them will be in its topic before the next one arrives because this is all a time-based operation. So for instance, your payment may have been in its topic for 1 hour when the new customer data arrives, or more likely vice versa. So there's a time component to joining data on a streaming platform. And there are extensions to the syntax in order to handle this. But you can basically trigger an event when basically when there are two matching events in two different topics, you can go and do something. Okay, and finally, aggregate. Aggregation is most useful for dashboards and monitoring. What exactly is happening on my system? Which metrics are trending up? Which metrics are trending down? And we do this by having windows. So there's a SQL extension for within X minutes, and we can have different types of windows where we're sort of sliding or hopping windows or session windows. And we can basically analyze our data in Windows as it slides along in order to populate dashboards or to create alerts or look for trends of anything strange happening on our system. KSQLDB is beneficial for Mojaloop teams because there's no JVM programming required. If you know how to write a select statement, then you know how to create a stream processor. Database skills are directly transferable, very rapid development and deployment cycles, and it's built in for integration and scaling. KSQLDB was written by a team in Confluent for Confluent's use. So it understands things like consumer groups and ACLs and replication factors, different serialization types, compression, all of these things, KSQLDB understands what they are. And the final one is Kafka Connect. So this is the fourth part of the Kafka ecosystem. And it's a way of integrating other systems with your Kafka systems without having to write code every time. Particularly, I would say, databases. So Kafka Connect lets you mirror a table from a database into a topic, or it lets you mirror a topic from Kafka back out to a database again by simply defining a job and running it on your Kafka Connect server. Kafka Connect itself runs as a VM. It can run as a single service on a VM, or it can run in a cluster. And again, like KSQL, it's a sophisticated service that understands Kafka. It's able to scale up and scale down. It understands access control and schemas and things like that. Once you're running the service, you can basically download and use source connectors and sink connectors. Many of these are open source. Some of them are partner supported and some of them are paid. The most popular one by far are the database source connectors in order to basically select or CDC from a database table and basically produce that into a Kafka topic. So as soon as the transaction gets committed on the database, it will be produced into the Kafka topic. And from there, you can do event-driven, you can trigger event-driven applications such as fraud detection, etc. Now, obviously, Mojaloop systems already have database systems and they're used for different functions. But this opens up the possibility of creating new data channels between the Kafka system and the database system, and indeed any external database system. So it's fairly common, for instance, to stream in, say, audit metadata from an external audit system into the Kafka system to build out stream processing rules. You may have things like employee, staff details, etc., that you might want to include in stream processing, etc. You can also read from files, from S3. It can connect to an FTP endpoint every 30 seconds and see if there's any new files and pull those files into Kafka topic. There are tens of different source connectors available. Sink connectors are streaming from a topic to an external system, such as writing to an Elasticsearch index or an InfluxDB table. You might want to use it for monitoring and write directly to a Prometheus system so that you can put it on a dashboard. So I used to do this quite a lot for clients, populating Grafana dashboards via Prometheus or populating InfluxDB time series dashboards via Kronos. Popular ways of sort of using real-time data from Kafka out to external dashboards. Kafka Connect lets you configure connectors basically using JSON. So it's a whole big bunch of parameters where you specify how you connect to your external system, the table or the file or whatever you want to use, and the topic that you want to use, and the various rules for how the connector should run. So it's useful to use. What I generally find is you need to have schema registry running before you use Kafka Connect in most cases. And that's because the most useful connectors are the database ones, and databases always need some form of structure. So they either need to write to the schema registry or read from the schema registry. But Kafka Connect understands the schema registry very well, and it has good tight integration with it. I would recommend considering Kafka Connect after you've been through a phase of setting up the schema registry and optionally a stream processor. What would you do with these additional Kafka services? Schema registry is really about governance improvement, bringing Kafka inside your change control system alongside your database, and basically assigning versions to your topics so that whenever you need to do a release that matches, say, a database release, then you can have it all part of the same change control step. You would use KSQLDB for doing things like filtering to subtopics. You might want to strip sensitive attributes from a topic before making it available to an application development team or to a partner. You could create region-specific feeds or compliance filtered streams. A lot of this really concerns obfuscation of sensitive data. You may want to transform, change the data types, change your timestamps from strings to timestamps so that you can do timestamp arithmetic on those. You may want to reorder attributes, rename fields for downstream compatibility with external systems. Both of these are quite simple to do and do not require much KSQLDB resources. The next ones, join and aggregate, start to get a bit heavier. KSQLDB does them and it's very capable, but it starts to require more resources on the KSQLDB server. So triggering new enriched streams when keys match across, I should say here, 2 different topics. So in a database table, yes, you can join many different topics, many different tables at once. In KSQL, the recommended approach is to join 2 at a time, like sort of keep layering a third and a fourth and a fifth onto the previously joined topics. This is very useful for anomaly, well, any irregular pattern detection. Joins are really essential. And then aggregation, count, sum, and user-defined functions if you want to create your own across Windows for just real-time activity dashboards. These could either be for monitoring for anything irregular or for management information about what's happening on the system in real time. And deploying many organizations use stream processing and they still build microservices. They use both together. The stream processing is very good at some operations. For instance, a stream processor does a join much more efficiently than, say, a Java microservice would do. So it makes sense to join both together, especially if you need to talk to external services or you need to do sort of different processing that's not easily achievable using a select statement, iteration, things like that. I would use Kafka Connect if you need to mirror data to database tables or object storage or analytics platforms. If there's data in a topic and you're trying to get it out, then this is the easiest way to do it. Or if you need to stream data from any external system into Kafka, particularly databases, then Kafka Connect is an obvious approach. And that's the first section. That's really to consider the additional APIs that are part of the Kafka ecosystem. They don't cost anything for you to use and deploy. They're not owned by Confluent. They're open source or community licensed, and they're available and ready to use if they're useful for you. I'm about to start on section 2, where we're going to drill down a bit more on stream processing. Are there any questions from anyone about that first section before we move into section 2?
Anyone want to raise their hand? No, I'm not seeing any questions yet, Mark. I'm sure they're piling up for the end. So please carry on.
All right. Thanks, Paul. Okay.
I'm seeing a lot of chat on various back channels, so people are very interested. Yeah.
Good. That's great.
Carry on.
All right. So let's talk a little bit about stream processing, which is the core of what I said we were going to address on the talk today. And an obvious question is, we already have a database. We're doing database processing. So how does stream processing differ really from RDBMS processing? I consider it an API for real-time data, whereas a database is really an API for stored data. You can only query data that's already in the database, whereas with a Kafka system, you're creating an API to react to data as it's already in progress. Databases are good for on-demand data retrieval using a select statement, persistent data storage with updates and inserts, and query-driven operations. This is familiar to us all. A streaming system is really for continuous unbounded data feeds. The data continues to be produced into topics as long as the producer applications are still running. And this creates different data access semantics because the data flow is continuous. Real-time processing, there always needs to be a sort of a grayed out asterisk after this. I mean, Kafka is not real-time. Very few systems are actual real-time. So there is latency behind this, and it is a case that a consumer only sees data after it has been processed by the broker. But it's really so close to real-time that for most intents and purposes, it is real-time. Now, this would differ if you're a high-speed trader and you're trying to have 10 microsecond access to data on a fiber from a stock exchange. They would not consider Kafka real-time. But for most intents and purposes, it's essentially real-time. And event-driven reactions, the idea that we're able to build an application that reacts to something rather than polling for something, which is what you would really do for a database. Databases are useful for point-in-time queries, historical data analysis, and OLTP transactions. And we're used to building client-based applications for databases. We're doing data analytics, we're using OLAP type queries, and for database processing applications, we're doing batch processing. Whereas Kafka, the types of operations that we're doing, certainly for Mojaloop, but this is ordered and resilient data buffering. This is the idea of using Kafka as a message queue, where you know that even if parts of the infrastructure or services are unavailable, we're not going to lose data. We're not going to get the order of the data mixed up. It's able to buffer all of this data until the consumers come back online and resume processing again. And this is sort of this is sort of Kafka 2011. This is what it was initially built for back in the LinkedIn days. It's useful for continuous processing. When we have an unbounded stream of data that we need to process 24/7, rather than data that we want to process once per day in an overnight batch, then we should consider using our real-time API rather than the database API. And for low latency processing, it is possible to have low latency from the database with OLTP transactions, and by repeatedly polling the database in tighter and tighter loops with better indexes and better tuning on the system in order to, say, perhaps query once a second or every half second or faster than that. And this was the sort of thing that I did a lot of when I worked for banks in the banking days, realizing that what I really needed was a real-time data API in order to get that low latency processing. And it allows you to build applications for continuous data pipes, which is essentially what Mojaloop uses Kafka for. But I'm proposing it can also be used to extend other applications such as fraud detection, etc. For building live dashboards, populating InfluxDB or monitoring dashboards, and for lower latency stream processing applications where you're saying, well, I want to have, say, a 3-second latency for my fraud detection rules. And I feel it's more achievable using the real-time data API rather than the database API. So in my opinion, both data APIs should be offered to development teams with design guidance on you should use the RDBMS API or the real-time data API for the different application requirements. So this sort of should be set out for the application development architecture. And yes, you may say, why use this for Mojaloop? And the reality is most Kafka systems are underutilized, in my opinion, especially in finance systems. Finance systems are not typically very high volume, but they are very important because they contain data about money. But compared with systems that are, say, used for advertising or instrumentation, the volumes are not comparably high. And actually, Kafka systems they were built from the start to have LinkedIn style capacity. And even quite a basic broker it should be able to handle 100 megabytes per second. As a general rule, the guidance that we would take is every topic partition should be able to handle 40 megabytes per second of producers sending data in. Now, you can check your monitoring systems and see what the peak capacity on systems is, but it's very normal on finance systems for peak capacity to be in kilobytes, say hundreds of kilobytes and maybe low megabytes per second. So there's actually a lot of headroom available on most Kafka systems. And I'm proposing, this is compute that you have already paid for and you've resourced. Why not use it to do additional processing rather than deploying compute elsewhere? Along the same lines, you're using existing infrastructure. The topics contain very rich payment data, clearly, in Mojaloop systems. And you already have all of the various other services and systems in place, such as network and security. These are ACLs, encryption, compression. All of this is already built into your Kafka brokers, and your stream processing is going to adopt all of these Kafka features as part of its processing architecture. So there's actually a marginal cost addition for putting the stream processing workload on alongside the Mojaloop workload on the same Kafka cluster. It does obviously require capacity planning and careful deployment, but I would say it's in most cases this should be feasible. Stream processing was created for money counting systems. That was the original purpose of this. Many other users of Kafka systems have some tolerance for data loss. There's some tolerance for data duplication. That's very rarely the case for systems that are used for moving money around. And it's also the case, that particularly payment systems, you do have compelling requirements for lower latency stream processing applications, probably more than any other industry. And everything is either open source or community licensed. So there are no license costs for deploying this. You don't need to go to a vendor in order to sort of buy software and get keys and get stuff set up and running. And arguably, I think Kafka is quite cool. It's fairly rare to get pushback from infrastructure and engineering teams if you're proposing to use Kafka for more. It's because it has a vibrant ecosystem. It has strong engineering pedigree. The Kafka project is still going really strong, and they're really thinking of ways to continue improving the system. So while there are various arguments for using different compute engines, you can't really say that the Kafka team are not innovating and trying to keep things as useful as possible for new users for the system. So in my view, there's rarely pushback from engineering staff to doing compute on Kafka systems as well. Just a little bit more on why do this for Mojaloop. Money systems generally have some responsibility when it comes to agile threat actors and building a platform that can react to any sort of irregularities that are happening on the system. This tends to fall into two different areas. One is any anomalous data. So this could be fraud. It could be related to releases. It could be anything unusual happening on a system, or it could be cybersecurity, any attempt to sort of break into a system. And I've spent quite a bit of time working with different banks on how to deploy these. And one example would be, using KSQL to do pre-filtering very close to the brokers with very low latency, and then say building out something like Yara or some other platform for signature matching. Or you could do joins on the system. These types of approaches are popular. And use stream processing as your foundation layer for the other systems that you will layer on afterwards. And data anomalies can be detected in multiple ways. Very basic statistical checks, like any SQL view, a where clause with mathematical functions, thresholds, ranges, things like this. Very easy to express as SQL. Window-based threat detection. Paired with frequency and pattern analysis. Normally we get 5 of these per hour. Now we got 12 of these in the last hour. Is that significant or not? Time-based anomalies. This is where using sliding windows and sophisticated sliding windows becomes very useful in order to detect that trends are changing trends of data patterns, I should say, are changing. Geospatial anomalies. If we're seeing transactions taking place and we have geospatial data available, and we're able to sort of do distance calculations between different transactions as they land into our topics, are we able to determine if something appears to be irregular or not. Statistical distribution functions. Now, KSQL does not have a lot of these, but it does allow you to plug in your own functions. You can write a Java function and plug it in. It's very common, for instance, for users to write tokenization algorithms in order to do obfuscation for sensitive data. So mask out names and addresses and phone numbers and things like that. In order to allow data to flow downstream, say, to test and development systems or partner systems and things. So it's one of the first functions we tend to see written as some sort of obfuscation to remove the sensitive data. But you can also write various other statistical functions that may be useful for you in anomaly detection. Plug these in and then call them directly from the select statement in KSQL. And various other advanced pattern detection by combining all of the above things. We find, I think the most impressive users in this area are really the usage of KSQL for credit card fraud detection. Quite a number of large banks have written large stacks of KSQL select statements using all of these techniques, creating flows of data in order to react to fraudulent activity for their credit card customer base. And this happens, in the United States in particular, where you have very, very large volumes of credit card transactions flowing in. The KSQL is popular in this area. Streaming data analytics, so risk scoring and alerting, financial intelligence, payment volume trends. Usually this is only useful if you're feeding it into some sort of a visualization or a real-time dashboard. So InfluxDB, Prometheus and Grafana if it's for monitoring, or some sort of a D3 charts, etc., depending on how you want to visualize that data. Sometimes it's CFO type monitoring to see exactly what's happening across the entire system. Other times it could be cybersecurity, engineering, different perspectives on the real-time data as it flows in. And some examples of the different types of systems. Somewhat surprisingly, different loyalty partner APIs has always been popular with KSQL. So being able to connect to external third parties in order to integrate their event-driven systems with our event-driven system and offer something in real time to the customer. So they spend money at a particular merchant and they receive a notification from that merchant's app. These types of integrations are popular. And offering open data APIs for universities, hackathons, these types of things. This is also possible using a streaming platform. It's very cool, particularly for if you're offering a hackathon for them to be able to do real-time transactions and see that data flow through an open data API. Okay, I'm coming near the end. I'm going to give just a slide on deployment, and then I'm going to show you an example of what of how you change a Mojaloop topic into a structured topic. Everything I've described today can be deployed in containers. So my recommendation would be, if you have Docker, to deploy a Docker container containing a schema registry service, a KSQL DB service, and if you need it or you want to use it, a Kafka Connect service. Schema registry is a very, very light service. It's really just a HTTP endpoint that accepts requests and says, here's a new schema, or give me the schema for this ID. That's all that it really does. It does not process any data, any payload data at all. It's simply metadata. So it's very lightweight and very low. It does not require much resources. It stores all of its data. It stores all of the schema data in one topic on the Kafka cluster. The KSQL DB container can operate as a single container or use two containers for fault tolerance. They will cluster automatically. Or you can create additional containers for scaling. So if you have a topic with 6 partitions, for instance, you can create 6 KSQL containers and will automatically scale, and each KSQL service will basically consume from one partition of the topic. So it's quite clever in how it's set up that way. Every create stream that you issue becomes a stream processor, and it runs on the KSQL DB container. So if you have issued 100 create stream statements in order to put structured data over topics and to create streams of streams. All of these will run as threads on your KSQL DB container. So it is a compute server for your system. It can be quite heavy. If it's doing lightweight streaming operations, it won't require much resources. If you start doing joins and aggregation, then KSQL DB will need to start storing data, not metadata. So it uses RocksDB, and it will require storage. But for transforms, for filtering, it's essentially stateless, and it's very lightweight. And Kafka Connect only it's a compute engine, and it does not store any topic data at all. It uses 3 topics for its own metadata, and you deploy Kafka Connect jobs. So you have a lot of network traffic passing in and out of a Kafka Connect container, but it does not actually store any data itself. You could run it on macOS, which is where I tend to run everything, or on a Linux VM, or on Kubernetes. If you don't want to use Docker, or you just want to deploy binaries, all of these are available as Linux or macOS binaries as well. Not Windows. It is possible to run this stuff on Windows, but it's probably more trouble than it's worth. Okay. We're coming near the end. I just wanted to provide an example of what this looks like. So as I said earlier, if you've ever issued a create view statement, then this should be very familiar to you. So here's an example of topic quotes put. We're issuing a create stream statement. We're going to store the data. We're going to serialize the data as Avro. And then we're going to basically select the attributes from JSON. So KSQL DB knows that topic quotes put contains data serialized as JSON. And it's going to look for an attribute called from, and it's going to store it in an attribute called quote from. 2 goes into quote 2. So here we're doing a transform in that we're renaming the column, the attribute to a new attribute name. And ID, we're not renaming, we're simply selecting an ID, and it'll be called ID. And then we start using various KSQL functions. Because the data is nested in a JSON structure, we're going to use extract JSON field. The top level is called content. We want to find an attribute called request ID, and we're going to call that request ID, et cetera, all the way down. Here, we're going to do a parse timestamp. We're going to find content.headers.date, which we expect to have in this format, and we want to convert it to a KSQL DB timestamp format so that we can do time-based arithmetic on this without doing any further parsing. Okay, here we are converting the content length into an integer, and we're converting sampled into an integer, et cetera, et cetera. So this is a definition that you would apply to an existing Mojaloop topic in order to create a new structure that can be selected from. Once you have created this, you can open a new KSQL session and say, select asterisk from topic quotes put, well, flat 6, I call it. And that becomes a continuous query. Then every time something is produced into that topic, that query will return another row of this data to you. And then that becomes a foundation for your stream processing layer. So the sort of basic layer basic foundation layer is to issue one of these for each of the topics that you want to use for stream processing. That's what it looks like. Just like a create view is deceptively complex when you start getting down to doing things, the same happens for a create stream. You can actually do an awful lot when you consider the different parts. The select list, all of the mathematical functions available in KSQL DB. I think it's largely modeled on Postgres. It doesn't have everything. So Postgres has text functions, geospatial, some other ones. But most of the mathematical statistical functions you will also find in KSQL. The where clause for doing a filter, the join clause for joining topics together, the group by for doing time-based aggregation, the window clause for specifying what windows you're interested in. Is it all the data in the topic, or just today's data, or this hour's data, or this minute's data? But there's no order by, of course. And here's the difference between a database and Kafka, because we're not querying stored data. We are actually processing streaming data. So we can't change the order, or the data comes in the order that it comes in, and there's no way of reordering that data. So there's no order by clause for a stream processing system. And once you've created a stream, you can feed another stream. And then you create layers of streams where data filters from one stream to the next stream. And you're doing some form of stream processing operation each time as it falls through the layers. And these are the types of systems that many of the banks have created in order to do anomaly detection for their credit card data by creating streams that feed other streams and go to different teams and different systems for different types of detections. For moving forward, you will find this and a lot more detail in that document. It's on Mojaloop. Let me dig it up and put it on the Slack again. We can probably put it into the channel for this talk. I would recommend creating some sort of a sandbox POC on Mac OS or Linux. Choose some topics, define topic schemas. You'll find a few more examples in the document I provided, and then run selects on those to determine if all the data flowing into those align to the same structure. You may find that the structure of some messages are different, and you may be able to filter those using where clauses and send them to a different topic. But if you find that there are many different structure types going into the same topic, then there might be a little bit of untangling to do in order to create the stream processing layer. If that's the case, please reach out to me on Slack. Quite happy to chip in and help and try to help you get that schema defined. If you can if you get to a sandbox POC and you understand the benefits that stream processing would build, then it's really a case of looking at streaming apps preparation, doing Kafka capacity planning. How much stream processing can you safely add to your Kafka cluster? What impact would that have? In terms of governance, resource usage, risk, continuity, all of these different factors to be considered. You may want to do stream processing on a separate cluster, which is perfectly fine. You could create a Kafka cluster just for stream processing if you prefer to have separation of concerns for that. Topic access control. How do you handle sensitive data? Do you want to offer streaming data via an API so that third parties are able to access it without having to use a Kafka client? Do you want to employ and use streaming data governance, and etc.? I've given a sort of a full list of the different items to consider if you want to sort of offer a stream processing capability within your organization. And that's it. I've run a little longer than I'd hoped to, but if you ever want to reach out, so you can reach me on Mojaloop Slack. I'm Mark Teehan. I've been there for a few months. Feel free to email me as well if you prefer that. And of course, we have time for questions now as well.
Thank you, Mark. Yes, we do have a few minutes for questions, but we do have a hard stop at the top of the hour. Does anyone have any questions for Mark before I start picking on people? Anyone want to raise a question?
I don't have a specific question actually, Paul, but so we have previously looked at integrating with FRMS. In fact, FRMS is probably the number one use case for us integrating with the main Kafka streams. I wonder, Mark, if you have any insights or recommendations, and anything we should be wary of, any kind of gotchas. But I mean, the pattern. There's two possible patterns that we have with FRMS. One is scoring after the event. So we would an FRMS would intercept our or actually just subscribe to one of our topics as a normal consumer on that topic, and they would kind of in parallel to our normal clearing flow, they would annotate the transaction with a fraud risk score, but not perform any particular interception. So the transaction would go through, but it would enable some business process to identify potentially fraudulent transactions that had happened in the past. The other one is the interception flow, whereby we would effectively break a topic in two and insert the FRMS between the two topics. So it would listen to clearing requests, score them, and then decide whether or not to pass them on to the clearing the clearing request queue. Are there any kind of gotchas you can think of?
It's fairly common to use stream processing in this area in order to standardize on some of these types of operations. So if you're going to open a consumer API to FRMS, then use stream processing to prepare everything that's needed for that data so that FRMS sort of has minimal processing to do. That's really just offering an API to an external party in the same way that you would to any other sort of external party. There's nothing specific to FRMS for that. Breaking the flow in order to let FRMS do scoring and produce back to another topic. There are transaction dependencies there that become very important to make sure that the things like fault tolerance, etc., and all that is really important. So as long it would need to align, have failover capabilities. It would have to have delivery guarantees, these types of things. And so making sure that they're the same standard as the other microservice producers that you have on the platform would be important. There's also concerns around things like what happens if FRMS is not able to consume. If there's any disparity between what it expects the structure of the topic to be versus what it gets. Use of a dead letter queue, being able to basically not getting stuck on one particular transaction, being able to move on to the next transaction even if something fails, and the sort of pattern that you would use for that using a dead letter queue. So I think the highest concern with that type of pattern would be having the highest level of fault tolerance so that the service remains online sort of no matter what's happening at the attribute level.
Okay,
Yeah,
thank you for that, Mark.
Thanks, Mark.
James, you want to follow up?
No, that's very clear. Thanks.
Okay, thanks. I'm afraid we are out of time now, Mark. We're right up against the hard stop here. So thank you for that. And I hope you won't mind if we send any follow-up questions via email or via the Slack channels. But thank you for that. I'll be posting the recording of this session on the Product Council Slack channel later today. So again, thank you, Mark. Thank you, everyone, for listening, and see you all again soon. Thank you. Goodbye.
Thank you, Paul. Thank you very much.
Thank you.